Hi, everyone. Give it another minute or so for folks to get into the meeting. Please, I can see you've already started. You guys know the drill. Please type your name into the chat for attendance. So welcome back. It's the final week of BWSI, and I'm sure you're all very excited. So today we have another just stellar speaker. We have Natalia Guerrero. She works at the MIT Kavli Institute for Space Research, and she's going to talk to you today about some work that's going on with the TESS Transiting Exoplanet Survey Satellite. So Natalia got a degree from MIT in physics with a minor in creative writing, and as you'll see through her bio, she has done a fantastic job of blending science and art and combining this into her technical work and also her professional work. After graduating from MIT, she spent some time on a project with the Royal Holloway University of London at the MIT Lab for Nuclear Science, and she was working on a detector for dark matter before she joined the Kavli Institute. She's been committed to creating interdisciplinary works of art and science. So as one example of this, at the last year's TESS Science Conference, she produced a musical piece called TESS, Songs from Extrasolar Spaces Concert. And she has been part of the Community School of the Arts, where she has developed curriculum and taught, and this is a branch of the Women in the Arts. And so you'll see that she is an amazing speaker with very, very broad interests. And today she's going to talk to you about some of the work on TESS. And her talk is titled Worlds Beyond Our Own, New Exoplanet Discoveries by NASA's TESS. So thank you so much, Natalia, for being here. Students, please text your questions or type your questions into the chat. And we're going to follow the same pattern of I'll call on you to ask Natalia your questions personally at the appropriate time. And so Natalia, over to you. Thank you so much for being here today.
No, thank you for inviting me, and thank you for the introduction, Jennifer. Okay, so as she said, my name is Natalia Guerrero. This is my second time speaking with BWSI, and I'm really excited to be back. So I'll go ahead and share my screen. Here we go. And is my title slide up?
Yes, we can.
All right, great. So this is what the view that you should have had this summer in Cambridge. This is from the top of the tallest building on campus, the Green Building, or the Earth Atmospheric and Planetary Science Department. And this is where a lot of people who are interested in planetary science, so studying our solar system, and some astronomers have their offices. But my office is actually over to the far right in the MIT Kavli Institute for Astrophysics. So I work on NASA's TESS mission, and I'll talk about that more in depth later. But first I want to take a bigger view, sort of like this is a bird's eye view of campus. I want to take a bird's eye view of this topic of exoplanets. So I want to start with a question that is sort of the heart of what exoplanet astronomy is, which is how unique is our solar system? I think it's a very human thing to ask ourselves what makes us unique as individuals, like where do we belong? And I think that's a question that can be applied very naturally to finding out where does our Earth belong and where does our solar system belong in the galaxy and in the wider universe. So first, let's get to know ourselves a little bit better. Let's get to know Earth. So take a look at this picture of Earth and take a second. What do you think? Maybe think to yourself, what makes Earth unique in this picture out in the vacuum of space? So right off the bat, I see that we have clouds hovering over our atmosphere, and we have an atmosphere, and it's rich in nitrogen and oxygen and all sorts of useful things for breathing. We have land, and what's more important is we have liquid water. And so you look at Earth and you can see these different things that make it a place where we can live. Now let's look at the wider solar system. We have rocky planets close to the sun, gas giants, sort of a bit further out, and then these smaller ice giants all the way out at the end, and then you get Pluto and the Oort cloud of distant objects, and those are rocky again. So there's a story here. We don't know how. We're trying to ask, how did these planets form? How did they form in the places they are? Why are some small? Why are some big? Why are these dense? Why are these so gaseous? So these are all questions that we're trying to answer. And now what we want to do is say, okay, we know that we are 8 planets around a star. If we look at other stars, what are we going to find? And the answer is more planets. Kepler, which was a space telescope launched back in the mid-2000s, set out to answer this question by staring at a select number of stars in a small patch of sky for a long period of time, for about 4 years. And what Kepler saw was that for every star, there is likely about 1 planet, which means that our galaxy is full of exoplanets. And what Kepler found was that a lot of these planets look nothing like the ones in our solar system. They're gigantic. They're close into their host star. They're really, really lava covered or have really interesting atmospheres. There's not a lot of, or what am I trying to say? No, there's a lot of diversity in the galaxy. And so we want to study that. We want to find out where we belong in this exoplanetary family tree. We've seen that planets form out of something called a protoplanetary disk, which is a layer of gas and dust orbiting a star. And as the gas and dust glom onto each other, that's where you start to get planets. There are small, dense planets, kind of like Earth. There are mini Neptunes, which we don't have in our solar system, so smaller than Neptune and cool, and giant planets resembling Jupiter. So these are some of our relatives that we are discovering through studying exoplanets. So let's talk a little bit about how do we actually image exoplanets. So this is a picture I took with a DSLR in a parking lot near my neighborhood. And this is a picture of Jupiter. And you can see Jupiter is this bright spot. And then around it are these 3 little spots, which are its moons. Now, Jupiter is really bright to the naked eye, but you can't see its moons. And then only with a camera are you able to see its moons. But it's so bright still that this moon and this moon are kind of hard to see. So this is a planet in our own solar system. Now try to imagine a planet next to a star, which is millions of times brighter than Jupiter. And we're trying to resolve a planet. Even with telescopes, it is impossible to resolve a planet and take a picture of it the way that we would a moon of Jupiter. So we have to be clever. We have to look at signatures that planets leave. So one of these is a transit. When a planet crosses in front of its host star, it blocks a small amount of its light. And so this tiny fraction of light is what we call a transit. And then when the planet passes behind the star, light is reflected off the star onto the planet. And so you lose an even smaller fraction of light. So transits of planets are usually about 1% of the light of the star is lost. This is very small. This is something we couldn't see with the naked eye, and it's still very challenging to measure with a telescope. So here we see another planet transiting a star. This is Mercury transiting the sun. You can see that it is you can't see any detail of Mercury, just that it's blocking some of the sun's light. So what we do is we plot this change in brightness over time, and this is called a light curve. A big planet will make a big dip, and a small planet will make a small dip. And depending on how close a planet is into its host star determines whether it's in the habitable zone. This is defined a few different ways, but the main way is whether the planet is far enough from its star that it's able to keep its atmosphere together, that it's not getting blasted away by the star's radiation, and that it's able to support some form of liquid water. So TESS is looking at stars that look more like the one on the right than the one on the left. The sun is bigger, it's bright, and it's yellow. And it's a planet that is small makes a small dip, and that's harder for a telescope to measure than a planet transiting a smaller, cooler star like this M dwarf, where the ratio of the planet's area to the star's area is larger. So you see a larger dip in the planet's light curve. So TESS wanted also to prioritize M dwarfs because they're the most common star in the solar neighborhood. So these are the stars within 80 light years of the sun, and we can see that the M dwarfs, which are these orange and red dots, are the most abundant near our solar system. And so just to show this a different way, we can look at the wavelengths of light. So the sun is over here in sort of the greenish blues, and M dwarfs are over here closer to 900 nanometers onwards. So TESS chose to a band pass, or the section of the visible spectrum that it was going to observe in, that included the spectra of typical M dwarfs. Whereas Kepler, which was looking for Earth-sized planets around sun-like stars, the peak of its observation of its bandpass was here, where sun-like spectra have their strongest point. And so this is one of the ways that TESS is sort of a little bit different from its big brother Kepler, and is trying to observe stars where it's easier to detect exoplanets. So I want to introduce you to TESS. TESS has 4 wide field cameras inside it. The spacecraft is about the size of a refrigerator. And each of these cameras covers 24 by 24 degrees on the sky. So we overlap the fields of view of each of the cameras so that we can see a big strip of the sky, what we call a sector. And so TESS observes a sector for 27 days at a time. And each sector, we stare and then step, stare and then step. So each sector gets 2 orbits or 27 days to observe. First, we started with the southern hemisphere of the sky, visible from Australia and South America. And then we went to the northern hemisphere, visible here in the United States. So our prime mission ended on July 4th of this year. And now what we're doing is we're going back to the south. The other thing I'll note is that you see these overlapping red circles here at the top and bottom. Those are the TESS continuous viewing zones. Sorry, I'll go back. So those are regions of the sky where TESS can observe continuously. It's able to look at those parts of the sky for almost a year total because they're overlapping fields of view. And so this is really exciting because we can observe planets that take longer to go around their host star, that have longer periods. So if you wanted to get a little bit of a physical representation for yourself of what 24 degrees by 24 degrees on the sky actually looks like, you can stick out your arm and go like this. And this distance on the horizon is 25 degrees, or about the size of the Big Dipper. So with that in mind, the fields of view of the TESS cameras are gigantic. This little cross is the Kepler field of view, and this is one TESS camera. So if you were able to map all of the TESS cameras onto the sky and spread it out, you would see that TESS observes a huge part of the night sky. Compared to Kepler and its follow-on mission K2, TESS is doing an all-sky survey. It's trying to see what kinds of exoplanets there are in every direction. So I'll pause here because we've covered a fair amount of ground. And before I dive into the nitty-gritty of how the telescope came together, maybe I can take a couple of questions.
Okay, so one of the questions that came in early is from Sajiv. Would you like to ask your question about Jupiter?
Oh yeah, I was wondering why these exoplanets and Jupiters these planets are so bright. Is it just like outgassing?
So Jupiter is bright because it has an atmosphere that reflects a lot of sunlight, so it has a high albedo. Yeah, it has a lot of, I think, like small dust and ice crystals in its outer layers.
So how long did it take to create the TESS camera assembly?
The whole thing, so from start to finish, TESS, I think, started getting designed in about 2008, 2010. And then from there, from the proposal getting accepted in 2010 to launch in 2018, it was 8 years of sort of design, development, building. And then I actually came in 2016 when we were starting to get the cameras for testing. So that final 2 years was all just testing.
Fantastic. Okay, I think we can move on.
All right, sounds good. So this is my favorite part of talking about TESS, is what the instrument actually looks like, because when I started working on TESS, I was actually in the flight testing team. So we were taking the cameras that were built at MIT's Lincoln Lab, the detectors were designed there, and then doing tests on them to see how they would perform in space and how stars would look in their fields of view. So this is a breakdown of what the different parts of the TESS satellite look like, what the science instrument is. So the cameras are these black cylinders. And so these are where all the lenses are, the black part, and then the silver part is where all the camera sensor and the camera readout equipment is. So this is all the camera assembly and then the lens assembly. And then each of the lenses is sort of capped by one of these sort of cones of shame. These are lens hoods, and they actually keep light from scattering into the camera when we don't want it to. So this is light reflected from this Earth or the moon. Light from the TESS is always pointing away from the sun, so it's never direct sunlight. But the Earth and the moon still reflect a lot of light from the sun, and we don't want that getting into the detectors because it will oversaturate them and blow out the stars that we actually want to see. And you can see that these are sort of set off at angles so that their fields of view overlap on the sky in the way I showed you in the animation earlier. And then all of the cameras come together on the camera plate assembly. And then this is put onto the spacecraft, and that has all of the propulsion fuel and the navigation and the way the reaction wheels to point the spacecraft. But this is where all the science happens. So to take a closer look at one of the cameras, TESS has 4 of these cameras. They have about a 10.5 centimeter diameter. So you could probably fit one in the mailbox. And they have 7 lenses that focus light onto this silver area right here. This is the focal plane. And so there's 4 CCDs, charge coupled devices is what CCD mean. And it's not a very useful acronym at all. They're camera sensors that are here. And then the light that falls on them is read out to these focal plane electronics. So one of the things that we were testing is this sort of white space between the last lens and the sensors is actually really important, because if that gap is too wide, the light goes out of focus before it hits the cameras. And if it's too narrow, it's the same thing. The light hits the cameras before it gets into focus. It has to be just right. And so when we got the cameras from Lincoln, we had to measure how well focused the light was in order to go back and say, you need to adjust the shim, the little piece of material between the lenses and the camera and the focal plane assembly. You need to adjust the shim by this amount. And what we're talking about is microns, tens of microns. So this is like width of comparable to width of several human hairs in terms of what we were adjusting in. So this was a very precise thing that we had to do and understand well. And these are the camera sensors themselves. So compared to an iPhone camera, these are gigantic. There are 2048 by 4096 pixels on each of these, and the pixels are designed not so much to capture a lot of detail, but to capture a lot of light. So really bright stars, all of their light can be captured completely in the camera without saturating and without losing any of that detail. So what does camera testing actually look like? It involves a lot of what we're now wearing every day when we go grocery shopping, PPE. So we wanted to keep the cameras clean, no dust or hair or skin cells falling onto the camera lenses and affecting our image. So everyone was dressed up in bunny suits, and this was in a clean room. And so here people are putting one of the cameras into a test chamber. So we named each of these chambers after dragons. I'm not really sure why, but I think this one is Norberta, which is named after the dragon in Harry Potter. And you can see Tess inside of it. Tess has a green eye because it's only trying to look at light in the red part of the spectrum, blocking out everything in the greener part of the spectrum. So this chamber is designed to keep Tess at vacuum, like space, and to allow us to pump in liquid nitrogen to cool the chamber to the temperature of space. The spacecraft actually keeps the cameras pretty warm, so we wanted to understand what temperatures we needed to set the heaters to and how much power that would consume. And then we tried to test the cameras by shining artificial starlight from artificial stars in through an assembly of an optical assembly. So this black thing is a fiber optic laser source that we could change to have different wavelengths, simulating different kinds of stars. And it bounced off a bunch of mirrors on this optical bench, finally off of this part of a parabolic mirror, and then onto a mirror that we could position so that we could bounce the light exactly where we wanted it on the camera focal plane assembly. And what you get is a picture like this of this beautiful constellation of fiber optic stars. And so this is actually a pretty sharply focused image. So this was a really fun part of the project for me. I actually didn't get to go in the clean room, so these are two of my colleagues. But just seeing the camera and imagining this thing that I'm working on now, that I'm taking images with now, that's 8 feet away from me, this is going to go into space and do these amazing things. And the cameras are also really fun because we would chill them to get them to temperatures that were space-like, but we would also take images with them at room temperature once they'd been installed in the chamber to understand if they were working. This was sort of like a health check. So what we would do is we would cover the window with a disc that had a little pinhole in the middle, and we would take a picture at room temperature. And very often these pictures were selfies. So this is a picture of myself with several other scientists. And the reason that it's blurred is because each exposure Tess takes is 2 seconds long. And so you have to stay very still. And we did not. So, but the stars don't move. So no blurry star pictures. After we tested all of the cameras and sent them back to Lincoln for the shims to be adjusted and for the thermal testing and vibration testing, they were packed up again and sent to Virginia, where they were assembled by Orbital ATK, which is now part of Northrop Grumman. And so so this is the cameras being assembled onto that plate that I was talking about earlier. And now TESS was getting integrated onto the rest of the spacecraft, wrapped up in some thermal insulation and lowered down. And you can see here, this is the radio dish that TESS uses to talk to Earth and to send us data. TESS was turned on its side, and you can see now a little bit more clearly the lens hood. And you can see that it has this sort of staircase pattern, and this is to sort of make light bounce away from hitting the camera itself. TESS's solar panels were also tested before it was packed up and sent down to Cape Canaveral here in Florida. So here's TESS on its fairing, about to be put into this Falcon 9, this big Falcon 9 fairing, and then it was driven out onto its out to be assembled with its launch pad. And it's really funny because TESS is so small, and this can fit a school bus in it. And then TESS launched back in April 2018, and I was able to attend the launch, and it is definitely a scary feeling to see something that you just spent many hours, many sleepless nights monitoring and testing go shooting off into space at hundreds of miles per hour. But it was also a very exciting feeling to look at it and say, hey, I worked on that, and we're gonna hopefully discover things that are really cool with the spacecraft. It was a really amazing team experience, and we got a lot of support from NASA leadership, from the science mission director, Tom Zurbuchen, and from the NASA administrator, Jim Bridenstine. So it was cool to see that they were also excited about this thing that our team was too. So what's TESS doing now? TESS has been orbiting the Earth in this elliptical orbit. The moon is actually in a resonance with it, so that helps keep its orbit stable. And one orbit takes 13 days, and during that time, TESS is staring out into that same spot. And then it turns around for about 8 hours and beams data back to the Earth. And so during this downlink is when we get data that TESS has taken, and then send it commands to take new data. So you can actually listen to TESS and see when it's getting data down by going to the Deep Space Network Now website, and you can see all their spacecraft when they're sending down data. But it was really exciting in the first few days after the launch, once TESS was in its initial orbit, to see, oh, hey, it's talking to us. It was really exciting. So the next part of my talk is going to be about how, now that TESS is orbiting, how have we been going from those big wide field images to knowing more about exoplanets? Any questions so far?
So we've got a whole bunch of questions. First question is from Emre. Would you like to ask your question about the comparison to other systems?
Sure. So specifically, what I was wondering was, in comparison to the upcoming James Webb telescope, how does TESS compare technically in the specifications and its capabilities? I know James Webb is theorized to be much more sensitive than current equipment. And after its deployment, how will TESS kind of work in conjunction, if at all, with James Webb?
That's a great question. So right off the bat, TESS is what's called a mid-X Explorer mission for NASA. And so that means that it's much smaller and much quicker turnaround. So, and then James Webb is a much larger telescope, and it is a much more complex NASA mission. And so it's a lot more expensive and has a lot more planning involved. So on the mission side, those are the major differences. And then on the instrument side, TESS is a wide field survey, and we are looking in the optical range. We have these 4 cameras that are very similar to digital cameras, whereas James Webb is going to go into space with a whole host of tools for looking at stars in different wavelengths, getting their spectra. And it's not just going to be for exoplanets. It's trying to look at all sorts of things, galaxies, stars. And so exoplanets is just one aspect. James Webb is actually a good follow-on to Hubble, because what it does is people propose observation plans for it and say, I want to look at this particular target for this reason. And then James Webb turns around and stares at that target for a specified period of time. Whereas TESS is just looking at one swath of the sky. And what TESS is hoping to do actually is discover planets in the areas of the sky that James Webb is going to also look at, and say, hey, this planet is really exciting because it has an atmosphere. We don't know what this atmosphere is, but we want to study it in more detail. And James Webb can say, okay, I can go look at that in far more detail than a telescope on the ground could. So TESS is scouting out exciting candidates for observation.
That's very interesting. Thank you.
Maybe two more questions. One, Emma, you have a question about the quality of the sensing?
Yeah, so you were talking about how it's easier to find some of the larger planets. So how small exactly can the planets, or can TESS detect, and does TESS ever find things that aren't exoplanets?
Yeah, so to answer your second question first, yes, we do. I'll talk about it a little bit later, but TESS has detected supernovae, and it's even detected a star getting sucked into, getting torn apart by a black hole. So anytime a bright object in the sky changes in brightness for some reason, and we happen to be looking at that part of the sky, we're going to be able to see it. But to go back to your first question, so TESS can observe changes in brightness that are about 1% a change in the star's brightness. So it depends on the size of the star to sort of limit what size planet TESS can see. But for, we've been able to detect planets that are about the size of Earth, for example, around M-dwarf stars. I can think of a couple of other examples later, but it's really exciting, the planets we've been able to detect. It can also detect changes in stars' brightness, flares.
Great. Okay. One last question sort of related to the sensor. It comes from Akshaya. Would you like to ask your question?
I was wondering, would small particles have an effect in the performance of TESS?
Like dust particles?
Yeah, because when handling the TESS itself down on Earth, you guys were wearing the PPV suits. So I figured that because it's so delicate, like how would it affect the performance very much?
Yeah, that's a great question. So we mostly want to keep things from falling onto the cameras because if you've ever looked through like your sunglasses when they're dirty, if there's like oil or dust on it, you can't see as clearly. And if you've ever taken a photograph with a camera that has dust on it, light bends around the dust and comes into the camera out of focus. And so that's one of the major reasons why we want to keep the outer lenses clean. And when TESS is floating in space, there's going to be space dust there as well, and we can't help that. But so far, that hasn't been a thing that we have detected or had an issue with. Although sometimes in some of the TESS images, you can see little tiny comet-like particles flying by in 1 or 2 frames, and they're like these little fuzzy out of focus blobs, and we call those fireflies. But so far, so good. None of them have landed on TESS.
Great. Okay, so there are some more questions that probably, I have a feeling you might answer some of them in the next part of your talk, and if not, we'll come back to them.
Yeah. Okay, so first let's look at what a TESS image looks like. So someone asked a question about, can TESS see stuff that's not exoplanets? And the answer very quickly is yes, because this is a comet that we saw in one of the first images that TESS took. And we weren't even taking science data at this point. This was just a calibration image to see how the cameras were doing after launch. And you can see the comet right here, and then its tail shooting out here. And this is NEOI's C2018N1. And I think the comet that everyone was looking at a couple of weeks ago was another NEOI's detected comet. So let's just take a look for a minute at one of the TESS images. This is from the southern hemisphere. You can see each of the 4 cameras with its 4 CCDs. And these bright patches that you see are the small and large Magellanic clouds. These are clouds of stars that form an almost galaxy. I think the small Magellanic cloud is a satellite galaxy. But you can see TESS is observing millions of stars, and each of these stars has its own story. It has its own flares, its own rotation behavior, and so we're just trying to hone in on as many as we can to see what is going on around them. TESS looked at single sectors for all of the south, and then turned around and looked at all of the north. And the reason that the northern hemisphere looks a little bit like a turkey is because there was a lot of scattered light I was talking about from the sun, from the moon and the earth, that were getting into one of the cameras because of how the orbit of the earth was lining up with the orbit of the spacecraft and the moon. And so we had to instead of looking like this, we had to move the cameras so that the third camera would be on the pole instead of the fourth camera. And that was just to avoid scattered light. So let's talk about honing in on a single star. So let's just pick this star, for example. This is what pixel data looks like from a given star. You see that it's not beautiful. It's not even like that picture of Jupiter that I showed you. It's a blocky pixels that are sort of changing in brightness over time. So you draw a box around those pixels and you count up all of the light that falls into them, and you graph that over time. And what you get is something that's called a raw light curve. And so you can see that there's some sort of periodic signal here. There's a gap where orbit 1 and orbit 2 happens. There's this big discontinuity. There's this mess here, which is likely the instrument moving a little bit. TESS has 3 reaction wheels, and it has to basically remove the what are called momentum dumps. They sort of spin up, and we have to dump all of that momentum at some point during each orbit. And so this is probably that. So we have to clean that up. We have to take all of those signals out with software, and we do. We get a flattened light curve, and we can still see some variability. But now what we have to do is search for something that looks like a nice transit in there. And by eye, it's very difficult to do unless the planet is large. So we use a model. We say, okay, take something that looks like a U shape and search for periodic occurrences of that. And then that's how we get a folded light curve, where we can see that there is clearly a transit, and it's happening many times over the period of an orbit. So each time there's a transit, we observe it, and then we stack all of those on top of each other to get this nice strong signal. So from there, we can say, okay, this is happening periodically. We know the size of the planet, we know the size of the star, we know Kepler's law, so we can figure out how far the planet is away from the star. That if we know the star's temperature, we can figure out the planet's temperature. If we know the star's mass, we can look at spectra from the star and how they shift from one wavelength to another as the planet tugs on the star, and we can figure out its mass. But this takes follow-up research. This takes help from additional telescopes. And so TESS is really a team-oriented telescope. We can find these light curves, but in order to get a picture of a planet, we need to work with other astronomers, with other instruments. So how did I do that? Okay, there we go. Here we go. So this is what a typical data report from a planet looks like. Our software generates a light curve where you can see the dips in each transit. These green lines indicate a given orbit. So this planet was observed in several sectors, so we have a bunch of data for it. This is the folded light curve where we can see the transit. And this one is more V-shaped than the other one that I was showing you, but we're still fairly sure that this is a planet. So we use software so this is where my team comes into play. So I manage the team that takes the raw data and the output of the raw data, which is all of these light curves. And we use software to cut down on the number of light curves, which is tens of thousands, to a more manageable number in the hundreds that we can look at by eye with a team of people who all have expertise in looking at these light curve reports. And we can say, okay, yes, we think this is a planet candidate. Let's release it to the community as a TESS object of interest, something that is high priority for other astronomers to observe. So these TESS objects of interest, or TOIs, go into this catalog. So this is like our actual website where we do this work. So we like leave notes for each other and for other observers and discuss these things together. And so we do this for hundreds of targets from each sector. So what have we gotten in the last couple of years? So TESS has discovered over 2,000 planet candidates. So things that we initially, when we got the data, thought were planets. So 26 sectors in all. Right now, we're looking at the data for the first time from the last sector that we took last month. And so we're going to find a few more planet candidates from the full prime mission. You can't find planets without also finding things that look like planets but aren't. So about a quarter of these planet candidates are actually false positives. So one of the things that looks like a planet transit is two stars going around each other, what's called an eclipsing binary system. Because when they block out each other's light, it is a transit, but often you can rule them out because they're much deeper and they're V-shaped. But sometimes it's harder to tell, especially if the star is faint or far away or really close to the star that we were observing. It's harder to distinguish, and you often can't tell until someone else goes and looks at it. But from the 1,500 or so that are planet candidates, there are 600 that are smaller than Neptune. Neptune's about 4 times the size of Earth. And I was talking before about needing to rely on follow-up observers. That is because it takes a long time to get enough data to confirm that a planet is real. So far, we only have about 55 planet candidates. That number is, I think, a bit higher today. I haven't updated this slide in a couple of days. It's about 66 papers that are out on these planets. But yeah, it takes a lot of time and a lot of teamwork. And it's actually something that we have college students and even high schoolers contribute to. So this is just another visual to show you what TESS has observed. As we've observed each sector, we get more and more planet candidates and discover planet candidates in previous sectors when we take closer looks at the data. So now I wanted to talk about a few of the TESS discoveries that have happened recently. And that is sort of the last quarter of my talk. Jennifer, I can take a couple of questions here, or we can just like go through to the end.
Maybe just one question. Mike Wimmer, would you like to ask about processing the data?
Yeah, definitely. So I was thinking about processing data, and I thought, well, artificial intelligence and machine learning is always great at that. So do you think that the use of AI or ML could eliminate the need for humans to analyze the data?
You are on the right track. So both the Kepler mission and the TESS mission rely heavily on machine learning to help us. So one of the tools we use to sift out from the tens of thousands of light curves is actually a machine learning tool. It's a convolutional neural net called AstroNet. And so that we trained it on 5 sectors worth of light curves that we went through and labeled ourselves visually. And then we used that training set to teach it to distinguish between something that looks like a transit and something that does not. Now we're labeling a new data set to make that even better, and also to eventually train it to distinguish between a planet transiting and something like an eclipsing binary transiting. So that's just one example that we work on with TESS, but other astronomers have other pipelines. But yeah, that's definitely a thing that astronomy is interested in, is training machine learning to detect planets. And TESS is great for that because we have all these light curves to use as a training set.
Thank you.
Yep. Okay. So I've kind of, so I'll go on to talk about some of the planets that TESS has discovered. So this is one example of a really interesting planet. This is a circumbinary planet that was actually discovered by a high schooler. These 2 stars are orbiting each other quite rapidly, and you can see that this secondary transit looks very much like a planet transit. And then when the planet actually transits, it's hard to distinguish it from the eclipsing binary signal. But a high school intern at NASA Goddard was looking through these light curves by eye and was able to see that this transit was sort of out of the ordinary, and realized that this is a planet orbiting a circumbinary system. a sort of Tatooine. And so that's the caveat with machine learning as well, is that humans will always be able to be good at spotting things that are unusual. And machine learning only is good at spotting what we teach it to identify. So that's TOI 1339B. I would like to apologize on behalf of all astronomers for not being creative with how we name things. The other system that I want to talk about was AUMIC. So I talked about protoplanetary disks at the beginning of the talk, and about sort of bright flaring stars. So AUMIC is a very bright star with a lot of activity. And so it was very difficult for astronomers to actually see the transit there. But when you flatten the light curve and do some processing, you can see that AUMIC B is this very small planet that is sort of getting blasted by this radiation coming from this planet. And NASA's JPL is always looking for new subject matter for its galaxy of horrors. So they made a poster, a movie poster as part of that, AUMIC Flares of Fury, because the star is so active that it's actively blasting away the planet's atmosphere, which you can see here. And this is a movie poster, and you can download this from JPL's website. But I actually got to help with the art direction for this. So working with an artist who was sketching things out for us and presenting concepts. And he was asking questions like, well, what color is the star? Like, what color can I represent the flares as? Like, what is a realistic way to show a planet's atmosphere getting dissipated? What angle should I look at this from? Like, should we do a top down? Should we be looking at it from the side, from the surface of the planet? So there were all these questions that were being asked that we needed to address. And it was just a really interesting exercise. And I actually invite you to do that if for one of your projects you want to imagine, how would I describe this to an artist? It really makes you have a different perspective of what it is you're studying. So I showed you TOI 1339. And so this last system is really exciting. This is TOI 700, which has 3 planets in it. TESS has found a number of multi-planet systems, over 60. And this one is exciting because the outermost planet that was discovered with TESS data is actually in that star's habitable zone. And this is going to be a really interesting candidate in the future for trying to do atmospheric characterization. All of the planets are small and Earth-like, or Earth-sized. And so this brings up an interesting question for astronomers studying formation of solar systems or planetary systems is, why are all these planets kind of the same size? Is that sort of a law of nature that when planets form, they're all the same size, or can planets form at different radii? So TOI 700D is the one that may have an atmosphere, may have liquid water, we're not sure. And so it's been illustrated to be this sort of blue. Someone asked a question at the beginning of the talk about what else can TESS look at? So TESS can also do astrophysics. It can look at eclipsing binaries. It can look at stellar flares. There's this really interesting astrophysics field called astroseismology, which is trying to look inside the hearts of stars and figure out at what frequency they pulsate, why they act the way they do. And because TESS can take data every 2 minutes for a select number of stars, we can get a very detailed sort of time-lapse image of what these stars are doing. But one of the exciting things that TESS can also do is figure out when a star gets really, really bright and often see what it's doing in advance of that. So this is a model of a star going supernova. And what you can see is that the brightness shoots up right here when the star explodes. And so, but there's this sort of time beforehand where we want to understand what was it doing right before it did this. And when observers on the ground see a supernova, they have to get really, really lucky to be happening to look at that part of the sky right before the star gets bright. But TESS has 27 days worth of data for a given part of the sky. So it is able to see what is going on before a star gets bright. And so this star's supernova curve looks different from this one. So this is inviting all sorts of interesting questions for astronomers who study this. And then for the other thing that TESS can observe is sort of these slow increases in brightness. And when this was first observed, I don't study supernovae or other astrophysical objects, so I would have had no idea what this was. But astronomers who were using all other telescopes to monitor black holes were able to say right away, this is a tidal disruption event. This is a planet getting sucked in, or a star getting sort of caught in the gravitational influence of a black hole and getting blown apart. And so TESS was able to provide a different way of looking at this system that astronomers observed with other instruments. So going back to this question that I asked in the beginning, how unique is our solar system? The answer is still, I think the answer is still, we're pretty unique. And we're starting to find systems that look sort of like ours, like this TOI 700 system. But our system, we have the great privilege of being able to study it in great detail. We're sending a rover to Mars, hopefully on Thursday. We've sent spacecraft all the way out to the edge of the solar system to take pictures of Pluto. So we're able to really understand well our solar system, and then we can continue to also investigate with exoplanet missions where we fit in this wider picture of planetary systems. So if you want to look at light curves sort of on your own, the Planet Hunters TESS project run by Nora Eisner at Oxford is a really fun place to go. They upload all of the light curves from the TESS 2-minute data, and have individuals from all over the world classify them. And sometimes those end up becoming real planets. They've published, I think, at least one paper and have maybe 2 or more in the works. So this is a really fun opportunity. TESS has internet presence. So if you're interested in learning more, these are the places to do that. Yeah, I've really enjoyed working on this mission for the last several years, and being a part of discovering new exoplanets and just seeing our own world totally different because of that. So thank you.
Thank you very much, Natalia. That was fantastic. I think we have time. We've had a lot of questions during the course of the talk. Maybe we can have time for one more question, which is a little, I guess, a little bigger picture. And Alexei Panis, would you like to unmute and ask Natalia your question?
Yeah, so this question I had was before you told us that the satellite goes around in orbit. So I was curious how far it travels. And I was curious, like in the case that you find a planet that is interesting and within range, like would you be able to, how realistic is it, or when will it be realistic to send people there to investigate?
Yeah, so the first question, so TESS travels out, I think, I need to double check, but sort of on the order of the distance from the Earth to the moon. That's about the extent of its elliptical orbit, but the moon sort of orbits in the plane of the Earth, and TESS is sort of at an angle. It has this elliptical orbit that's off from the orbital plane of the Earth. But yeah, your second question is interesting because TESS is looking at stars that are comparatively nearby. They're only maybe 100 parsecs or so away, or 300 light years or so away from our sun. But those are still really far. So I think the closest stars, like, so let's say 5 parsecs, like Alpha Centauri, I think it's still going to be a long time before we can send humans to these places, maybe centuries. But there's already really interesting technical experiments being developed to send really tiny probes like I think it's called Breakthrough Starshot, maybe, to send little tiny chips propelled by giant lasers to these systems to take initial data. Maybe that'll happen. I think the thing that might happen sooner is being able to take an actual picture of an exoplanet. One of the missions that I'm really excited about that's sort of often been proposed is Starshade, which is real, just like the technology is really cool, of having a telescope like James Webb or like the Roman telescope out in space, and then millions of miles away from it having a gigantic starshade, like twice the size of a football field, and moving that into position such that it blocks out the starlight so you can see the planet, and then being able to directly image a planet using a starshade. That's one of the technologies I am so excited about, and I really hope is able to become a reality.
This is all very fascinating. Thank you.
Mm-hmm.
Thank you, Natalia. I think right now I'd like to turn it back to Lisa, who is going to call in a couple students.
Yes, Clarice Liu, you can go first if you're there.
Oh, sure. Thank you so much for such a fascinating talk on astronomy. I really, really admired the intersectionality in your career, especially with like all the arts and the analytics and the imagination and everything that just goes into making something as innovative as TESS. It's just a really, really nice and refreshing perspective on planets, and especially that photo of Jupiter, you know, something that we all expect to be so large and just so there to be so tiny, and just like so much information that has yet to be found about it. And it's just, and all the diagrams you showed, those were some of the most beautiful visualizations I think we've seen this entire session. And it really just goes to show like how far we've come in technology, but how much further we have to go. In addition to that, thank you so much for like always reminding us to think of the fundamentals of why and how we're going to do science, which is to always learn more. So, you know, reinvigorating that kind of diversity and magic when you combine the STEM and the arts is something we're all going to carry forward with us for the next 4 days at least. And, you know, we're definitely going to listen to TESS and download and stare at that flurry poster for whenever we get the chance, and keep working together to find the answers to stuff we don't know. So yeah, thank you so much, and good luck on Thursday.
Yeah, thank you. I appreciate that.
And then we're gonna have Alexander Hutchinson.
Like Clarice said, thank you so much for coming to give us your talk about space and the results of TESS's mission. It was super, super interesting to hear about how TESS used its 4 cameras like to observe space and the exoplanets, as well as learning about the precision required for the cameras to effectively capture the light from the stars. And not to mention seeing like the results, such as like the comet and the calibration photo, and the clouds of stars, and especially the black hole pulling in the star. That was all super, super cool. And the process of confirming like a target of interest as a planet candidate, it was super, super informative, and I'm sure we're all really grateful to hear about this talk from you. Thank you so much. Also, BWSI is presenting you with BWSI shirt.
And what do you know? I have it here.
Amazing.
Thank you so much.
Thank you again, Natalia. This was
Thank you,
fantastic.
Natalia.
Really appreciate your time.
Yeah. I'm really excited to see what other questions you had. Last year, the students had all these amazing questions that made me think a lot about what the work I'm doing is and how to better communicate that. So I'm looking forward to scrolling through those as well from you guys.